So t-test compares the means of two groups. It answers the question something like, is observed difference statistically significant? It has three types: one sample t-test, two sample t-test, and paired t-test. We'll talk more about all these types shortly. The t-test assumes three things. First, data are roughly normally distributed, especially in small samples, though with large samples it is more forgiving. Second, each observation must be independent of each other. And third, group variance should be similar. If not, we use other non-parametric tests. More on these assumptions when we will conduct the t-test. Go to Task and Utilities. Under Tasks, under Statistics, double-click on t-tests. That will open up a middle pane. Make sure that fhs_lib.heart dataset is selected. Keep the t-test under roles as one sample t-test. Let our analysis variable be systolic blood pressure. And then under Options tab, under Test, under Tails, we keep two-tailed test. And alternative hypothesis mu, that is the mean, is not equal to, this sign means not, is not equal to, I'm sorry about that, in a second, is not equal to 120 millimeters of mercury. Rest of the options we are going to keep as default. In fact, what we are trying to see is that if our mean systolic blood pressure of all the individuals in Birmingham Heart Study data is equal to 120 or not. So our alternative hypothesis here is that it is not equal to 120, and that's all. Let's run this test. Okay, so here are our results. We will ask ChatGPT to interpret them for us. I'm just gonna open these results in a separate tab. Control A to select all these results. Control C to copy, and then I'm gonna paste them in ChatGPT. Okay. So here are our results. Okay, so the descriptive statistics is here. Total number of individuals, 5,209. Mean systolic blood pressure in our data set is 136.9 millimeters of mercury. That, like we have seen it so many times. Standard deviation 23.74. Standard error this. Minimum maximum values 95%. Confidence interval of mean is this. Okay, interpretation is this. Mean systolic blood pressure has 36.9, which is above the mean. Okay, and then normality. The next is the normality test. We see that all these are below the 0.05 threshold. The interpretation is that all tests are strongly rejecting normality. So, but this is not surprising. We are fine with non-normality in this case because we have a very large sample. But if we had a small sample, we need to run non-parametric tests at the same time. Okay, so here are our main results. One sample t-test. We see that the t-value is 51.4, which is huge. If it is more than 2, it is indicating a statistical significance. The t-value is less than 0.05. In fact, this is even less than 0.001, which means that the mean systolic blood pressure of the individuals in our Birmingham Heart Study dataset is statistically significantly different from a normal systolic blood pressure, 120 millimeters of mercury. The clinical significance of is that the data in our Birmingham Heart Study, the collection was kind of biased because the people who have the tendency of higher systolic blood pressure are are enrolling in the study much more than those who were uh, normal or slightly lower side of systolic blood pressure. We're gonna talk more about them later, but what I wanted to show you over here is that how to conduct t-test and how to interpret the results. When you copy paste your results directly from a SAS, for example, by Control A, Control C, and Control V, it does not automatically will paste all the images or the visuals over there. So one way around is to just copy each individual image from your SAS results and then paste them there, and just submit them as right after you paste them, and it should give you the interpretation of those results without even asking any specific questions. Same word for the QQ plot, copy image and paste them there. Okay, and here are the interpretation of those results. We see that the systolic blood pressure is approximately normally distributed. The red line, the kernel curve, is the expected. Sorry, the blue line, the is the normal distribution, but the red line, the broad dark brown line, is the actual normal distribution. And we see that these are two separated, which indicates that they are not ideally normally distributed, and that's what we see here in the interpretations also. Okay, and then here are the plot which we call the QQ plot. We see that ideally all these values should be on this oblique line, but we see that it is deviating at both the extremes, at the lower values and also at the higher values, which is again an indication that the data is not normally distributed. Since our data was not normally distributed, we have to conduct what is known as non-parametric test. To do that, we'll keep all the options we have previously as such. The only thing which we are going to change is to check this box, non-parametric test, signed, tested with Coxon, signed rank test, and then submit the code again. And at the bottom of our interpretation, now we see an additional table. I'm just going to copy this table, Control C, and paste it in ChatGPT and get the interpretations right there. Okay, so it is generating our results. We see that non-parametric test compares the number of values above and below 120 millimeters of mercury, and we see that here are the non-parametric test results. Non-parametric test considers both direction, magnitude, or difference. Also highly significant, confirming that central tendency of systolic blood pressure is above 120 millimeters of mercury. So summary of statement: all three statistical tests student t-test, which we conducted previously, sign test, and Wilcoxon sign rank test showed that the systolic blood pressure in this sample is significantly higher than the hypothesized 120 millimeters of mercury. Okay, so what I wanted to show you is that if you have non-normally distributed um, data, as was the case in Framingham Heart Study, although it was sufficiently large sample, it is always good to conduct both the parametric and non-parametric test being the t-test and non-parametric test being sign test and Wilcoxon sign test, and present the results from both these tests as we did in this case, and we found the same results here. But there would be situations when you will have conflicting results. With parametric test t-test you might have, say, no difference, and with non-parametric test you get statistically significant difference. So in that case, if the data was non-normally distributed, you will choose for non-parametric tests as your final decision. For two sample t-tests, instead of um, one sample, you will choose two sample t-test, and that will pop up a new field under under roles. We'll keep the analysis variable as systolic, and the grouping variable, let's choose sex. We want to see how much was the difference in mean systolic blood pressure between male and female, and if the difference was statistically significant. Under the options tab, I'm just going to keep the alternative hypothesis. There is the mu minus 1, that is the mean systolic blood pressure of males versus mean systolic blood pressure of females is not equal to 0. So the difference is not 0. So that's our alternative hypothesis. Okay, and instead of default plots, I will choose some additional plots. I will keep histograms and box plot, normality plot, confidence interval plot. Wilcoxon box plot we'll use when we will conduct the non-parametric test, and then I'm going to submit the results, submit the code. Okay, so here are our results. I'm just open them up in a separate tab, Control A, Control C, and open up a new ChatGPT query, paste my results here, and let the AI use their magic. Okay, so normality test, that's our first table here. We already know that, and this says less than 0.01. That means that the mean systolic blood pressure of either of these groups was not normally distributed, as we see it here. Also, let me make it bigger. Okay, so for the females, we see that all of these results are below 0.05. That means that none of the distribution of female systolic blood pressure was not normally distributed, and same was the case for male. It was also not normally distributed. Okay, so then the next table, the descriptive statistics, compares values separately for males and females. 1,873 females, mean systolic blood pressure this, standard deviation this, minimum maximum values, and here are the values for males. And the mean was identical. The variability is higher in females because we see that the standard deviation for a female was higher. And when we compare the mean, we see that there is a difference of 0.05 millimeters of mercury. The females have 0.05 millimeters of mercury lower systolic blood pressure than compared to males. Very small difference. And here is the 95% confidence interval, and we can just right off the bat see that these values contain zero, meaning that the difference is not statistically significant. And we do also have the p-value here, which is above 0.05. So there is no statistically significant difference between the systolic blood pressure of males and females. And this is going to be the interpretation by ChatGPT. Mean systolic blood pressure is the same in male and females. Females show a slightly greater variability and so on. So since this data was not normally distributed, we are going to conduct a non-parametric test, Wilcoxon rank test, and we're just gonna we're just gonna check this box, and we're also gonna check the Wilcoxon box plot also and submit the results. Okay, so here are our results, and the non-parametric tests are here. Okay, let's choose all of them, select all of them and paste them in ChatGPT and see what ChatGPT is going to tell us. In fact, I'm going to read the interpretations from the bottom, which should be the case in most of the scientific studies. You normally start with reading from the conclusion. Okay, the summary is that no sex difference in mean systolic blood pressure by t-test, but we do see significant sex difference in distribution, shape, and length by the non-parametric test. So practically men and women have the same average blood pressure, but the pattern differs. So women shows wider spread, more low and high values, while men have values are clustered more tightly around slightly higher rank. So we can ask ChatGPT what is the final interpretation. Okay, so what is the final interpretation? Is there is a statistically significant difference between male and females, or it is not? Tell me both by parametric and non-parametric test. A great question. By parametric tests, and the interpretation is that men and women have the same mean systolic blood pressure, and by non-parametric, there is a significant difference between sex. So if you care about means, there's no significant difference, but if you care about overall distribution, there is a statistically significant difference between male and female. Bottom line, no difference in average systolic blood pressure between C, but the distribution is differs significantly. Let's also take a look at the visuals. We see visibly that the mean systolic blood pressure of females is slightly towards the left side, meaning towards the lower values than the distribution of systolic blood pressure for the males. And even the box plot at the bottom, you see that the mean is very at almost the same levels for females and males, but the median, which is represented by this vertical line, in this case mostly when the box plot is vertical, then this line is obviously horizontal, but here it is in the horizontal position, so the median is in a vertical line, and we see that the median is much lower for the females compared to males. Okay, and we also see that female, the values are much more widely distributed compared to males, which have the values much tighter together. Okay, and here is the visual of the confidence interval. You see that the confidence interval is crossing the zero neutral value, so indicating that this difference between male and female was not statistically significant. QQ plot we previously discussed, it is deviating at both extremes at the higher level, higher values and the lower values, and is following the normal distribution in the center. Paired t-test is conducted when you are comparing the same population with itself. For example, say you have 50 individuals, and you check their systolic blood pressure, whichever it was, and then you give them some medication, and then you check their systolic blood pressure again after say 1 hour or 2 hours of giving the medication. In this case, you are comparing the population by itself, the systolic blood pressure before the medicine and after the medication. So the only difference would be from the other sample t-test would be that the formula to calculate the standard error will be slightly different because you do not want to factor in the distribution of the same sample again and again. When you are comparing males and females, you have to factor in the distribution of the standard deviation among males and standard deviation of the females while calculating t-test. But here we have the same population, so you do not want to factor in the deviation, the standard deviation twice. For those reasons, the formula becomes slightly different, but the interpretation remains exactly the same. So in case of paired test, you just choose paired test, the grouping variable one. I mean, Framingham Heart Study data is not structured for such kind of analysis, but we are going to assume that before giving the medication, the blood pressure was this. I know it's just diastolic blood pressure, but just let's assume this was the systolic blood pressure um, before giving the medication. Let's use systolic, in fact, sorry. Okay, so we see that it was high, and then these individuals were these 50 individuals or whatever number of individuals they were given some medication, and after 2 hours, we checked their blood pressure again, and it was this value. Okay, this is diastolic, but assume that this is the systolic blood pressure after giving the medication. We're gonna keep all the values the same and submit the code. Okay, so here are our results. We see that as expected, the difference is less than 0.001, which means that our medication has worked. It has brought down the blood pressure significantly, statistically significantly reduced the blood pressure by, in fact, 51 millimeters of mercury, which is kind of unrealistic. But the point is that we just wanted to learn how peer t-testing can be conducted.